Oh, hi there. Nothing like corn fresh out of the can. Of course, cans, cylinders, make me think about optimization and optimization problems. You see, there are lots of different shapes of cans. Some cans are kind of tall and skinny. Others are sort of short and wide. In fact, two cans might have the same volume, yet still be different dimensions. You know, have a shorter height or a larger radius or whatever it might be. Now, just because two cans have the same volume doesn't mean they have the same surface area. The surface area might be different. So a simple optimization problem, one that you're probably a little bit familiar with, might be if the volume of a can, in this case my corn, is 540 centimeters cubed, or 540 milliliters, if that's its volume, then what height and what radius would minimize the surface area of the can and therefore make the can less expensive to manufacture? That's an optimization question. And optimization questions are always about finding a maximum or a minimum value. And so when we go to solve an optimization problem in this course, we're going to start by defining an equation that will represent the problem, and then using our algorithm for extreme values to find the maximum or the minimum value that that function takes on. And we know that maximum or minimum values of functions either happen at the end point of the function, my two green vertical lines here, or at one of the critical points. In this case, that could be right here. There's a maximum value. So let's take a look at some simple optimization problems, and then we'll take a look at this can of corn example as well. Come on, let's get to it.
So the first optimization problem I'm going to work on involves area. So we have Keith, who owns a dog kennel, and he's going to create a fenced-in area along the side of a barn for 4 dogs. He has 200 feet of fencing to work with, and he wants to, of course, maximize the total fenced-in area. So we're going to come up with an equation that's going to model this situation. So let's just look at these dog pens. They have a dimensions, a length, and a width. I'm going to call this value y, and I'm going to call this x. And I'm going to say x goes from here to here. Now notice that maximizing the total area of 4 dog pens is exactly the same as maximizing the area of each individual one. So the total area is x times y. This area function is our function that we want to maximize. Now we're going to find that when we work on optimization problems, the problem that we run into right away is we have too many variables here, x and y. So we need to relate x and y so that we can just have one variable. Well, notice that if we have 200 feet of fencing to work with, we have another y value here, and here, and here, and here. So 200 must equal x plus 1, 2, 3, 4, 5y. Okay, remember you're not going to use fence along the barn side here. So in order to take my area formula and make it simpler, I can actually write everything in terms of y, because this tells me that x is equal to 200 take away 5y. Plug that in for x into the formula for area, and I get 200 take away 5y times y. If I want, I can simplify that. And now I have a simple area formula with 2 variables, a and y. And I want to know, when is the area a maximum? Well, this is a question that you've actually looked at possibly in grade 10. Because this is a quadratic equation, it's just a matter of figuring out where the vertex of that parabola is and then realizing that's where your maximum area is. So it's a parabola. If we graphed it, we find it does this right here, where this is y and this is a. However, we don't need to find the vertex by completing the square or doing anything fancy like that. We can actually just use calculus, because we know that the maximum of this function is going to occur at the critical point. So we take the derivative and we set it to 0. So dA by dy is equal to 200 take away 10y. When is that equal to 0? Well, that happens when 10y equals 200 or y equals 20. Well, if y is equal to 20, x from up here is 200 take away 5y, so x would be 200 take away 5 times 20, or 100. And those are both in feet. And so we're able now to describe what Keith's dog kennel or fenced-in area should look like. He should have 100 feet right here, and then 20 feet right here, and then 20, 20, 20, and so on. All right, let's look at our next example. So let's take a look at this can of corn. The volume of the can of corn is 540 milliliters. Now, a milliliter is the same as a centimeter cubed, so we can say 540 centimeters cubed. Now, we need some measurement formulas. The volume of a cylinder is equal to pi r squared h. That's just the area of the circle, okay, times the height of the cylinder. Now, we know that the volume is 540, so we do have this formula right here to work with. So let me just fix that. Now, that's not the formula that we're looking to find an optimal value for. We're actually interested in the optimal value of the for surface area. So the surface area is what we need to look at. Now, the surface area of a cylinder is 2 pi r squared. That's 2 times the circle that makes up the base and the top, so 2 times pi r squared, plus the lateral surface. Now, the lateral surface is made up of a rectangle where one side of the rectangle has the height of the can, and the other part of the rectangle is actually the circumference of the circle. Now, the circumference of a circle is 2 pi r times by height gives you the area of that rectangle. So there again, that's your base and top, and that's what's called your lateral surface, which in this case is a rectangle. Okay, so surface area is actually the formula that we want to, in this case, minimize. Its formula is 2 pi r squared plus 2 pi r h. Again, I have too many variables. Okay, I have one variable for the area, and I have a height and a radius. But if I look back over here, I realize I can actually solve for my height or my radius. A little easier to solve for height here. This tells me that the height is 540 divided by pi r squared. And now I can take that and I can actually sub it into the formula for the surface area. And let's just take a look at what that looks like. So when I first sub it in, that's what I get when I sub in h equals 540 or pi r squared. And I'll just simplify a little bit. So the pi divides out, and so does r and r squared. And 540 times 2 would be 1,080. So I get that right there. That is the formula now that I want to find the optimal value for. And so I can do that, again, by knowing I know the optimal value for this has to occur, the minimum value in this case, has to occur at a critical point. So I'm going to take the derivative and set it to 0. So dSA by dr is equal to 4 pi r minus 1,080 over r squared. Keep in mind that that's 1080 r to the power of -1. When you take the derivative of that, you get negative 1080 r to the -2, or 1080 over r squared. Set that to 0. And I get 4 pi r equals 1080 over r squared. Multiply by r squared gives me 4 pi r cubed equals 1,080. Divide by 4 pi and take the cubed root. So that, of course, simplifies to the cubed root of 270 over pi. If you figure that out, I believe you'll get a radius of approximately 4.41 centimeters. Now we can also solve for the height, since we know the height is 540 divided by pi r squared. Once we have our answer for r, in this case I'm just going to do an approximate answer. 540 divided by pi times 4.41 squared. That's really close to 8.8 centimeters. Now, you'll also notice those values are about double each other. So the radius, it appears, is about half the height. In fact, one thing you learned probably in grade 9 was that an optimal cylinder actually has a height and diameter that are equal. And sure enough, that's exactly what we got here. You were just told that as a fact in grade 9, but now using calculus, we can actually show for this can why that has to be the case. So let's take a look at our can. What is its actual height and radius?
Let's take a look at this can of corn. If I measure across the diameter here, I see my diameter is about 8.5 centimeters. That makes my radius about 4.25 centimeters. And my height is 11.5 centimeters. So this can of corn is not an optimal shape. Now why is that? Well, there's probably lots of reasons why it's a little taller and skinnier. It's easier to hold. Might have something to do with how it fits in a box. But there are other issues as well. Consider why a tuna can might be so flat. Definitely not optimal. However, notice that the flatter a can is, the smaller the label is, and the label's expensive to make too. And take our orange juice. The base and the top are made out of aluminum, and the lateral surface is made out of cardboard. Now in this case, certainly the base and the top, we would think would probably cost more money to make than the lateral surface. Well, we can take a look at a question like that too. Come on, let's take a look.
So let's take that orange juice example and let's make an assumption. Let's assume that the aluminum is 3 times more expensive than the cardboard. And we'll say that the container has a volume of 350 centimeters cubed. Okay, so volume, pi r squared h. Of course, we know 350 equals pi r squared h. And we can say the height in this example is 350 divided by pi r squared. Now, we don't want a surface area formula. What we actually want is like a cost formula. So the surface area formula is, of course, 2 pi r squared plus 2 pi r h. But we know that this is a bit kind of a bigger value. So what we're going to do is we're going to introduce a constant. We're going to say let k equal the cost per centimeters cubed of the lateral surface, the cheaper surface. Now I'm using k. It is very common to use k when in calculus when you really want people to realize something is a constant, because that matters when you take a derivative. So if that's our surface area formula, let's change it to a cost formula now. So the lateral surface is going to cost 2 pi r h times k. But if the base and the top are 3 times more expensive, then we take 2 pi r squared and we times that by 3k. And then we can simplify that and it looks like this. 6k pi r squared plus 2k pi r h is the cost of making the can. Now, of course, there's a lot of variables in that, not as many as you think, because keep in mind, k is not a variable, and neither is pi, but we have an r squared and we have an h, but of course we can use this equation to replace h in the equation. Just like that. Okay, do a little bit more simplifying, and you end up what we end up getting for our cost equation. So this represents some graph. And that graph will have a minimum or a maximum value that must occur at one of the critical points. So let's take the derivative, set it to 0. So dc by dr would be, keeping in mind that k is a constant, you're going to get 12k pi r. Keeping in mind that this is like r to the power of -1, gives us -700k r to the power of -2, or r squared. Critical point when that's 0, so we set it to 0. Rearranging and solving. Now notice something interesting happens here. The k's actually divide out. And so we don't need to worry about the fact that we didn't actually know what k was. We didn't actually know what the cost per centimeter cubed of either the lateral or the base or the top was equal to. Here we're going to get 12r cubed equals 700. Divide by 12 and take the cubed root. The radius of this is going to be the cubed root of 700 divided by 12. That gives you approximately 3.88 centimeters. Now we can use that to find the approximate height as well, because keep in mind our height, 350 divided by pi r squared, is now going to be 350 divided by pi times 3.88 squared. Just use my calculator to figure out what that is. And that gives you about 7.4 centimeters for the height. So 7.4 and 3.88 centimeters. So not surprisingly, this can is slightly skinnier than the regular optimal can because the base and the top cost a little bit more money to make. Let's actually go back to the can of corn example and look at the formula we came up with right here for the surface area just in terms of the radius. I mean, that's probably the most difficult part of an optimization problem, is just getting to that place where you have that formula. We found the minimum value for the surface area by taking the derivative and setting it equal to 0. Let's look at the graph of the surface area in Desmos. Here it is. And sure enough, we found a minimum value. There it is right there, 4.4. And then that 367, that must be our minimum surface area. Now, how did I know that this was a minimum? Well, from the graph, it's pretty easy to see. I mean, there's no negative values in this example. Okay, so r can't be negative, so none of this stuff counts. If we look at this formula, it's pretty clear to see that as r gets really, really small, the surface area gets gigantic. Okay, as r gets small, this approaches 0, but this approaches infinity. And so it's not shocking that our surface area, as the radius gets really, really small, our surface area just shoots off. The other way around is true too. If the radius were to get really, really big, okay, this part of the formula approaches 0, but this part approaches infinity, and so the graph gets really, really big as the radius gets bigger as well. Other ways you could convince yourself that this value was a minimum value, you could technically do the second derivative test and see that you have a local minimum, but man, that's a lot of work. So I wouldn't recommend that. And if we go back to our area example, the first example, here's our formula right here. And we set the derivative and we set it equal to 0. Now that one we knew represented a maximum area because we have a pretty good idea what this parabola looks like. We know it's a parabola that opens down and therefore it has to have a maximum. But we could kind of do the same thing. We could say, look, as y gets really, really small, the area gets really, really small. And as y gets really, really big, then the area gets really, really small as well because this -5y squared becomes a very, very large value. I'm just basically saying why I don't need to worry in this case about checking endpoints of the function. When I gave you the algorithm for finding extreme values, you had to check the endpoints and you had to check the critical points. Whereas in this case, in measurement kind of examples, the endpoints are always either for areas of 0 or for, you know, surface areas that get closer and closer to infinity. So you don't need to worry about it as much. Okay, I've given you some questions to try. These are challenging. Optimization is a difficult topic, and you're gonna have to try your best on these, and I will get some full solutions up for you to look at as well. And that's kind of how you learn this topic, just by trying these out and seeing, developing some problem solving skills. So good luck with that, and try your best, and I'll see you again soon.